I'm going to talk about area between curves. This is going to be fairly long, I think, so at least for the video part of it. So I'm going to split this into a few parts, and the first one is just a theoretical discussion, so I'll call that as part one. Here we go. Suppose the problem is that we need to find the area between the curves y equals f of x, this top curve, and y equals g of x, the bottom curve, on an interval a to b. So x equals a to x equals b. We need to find the area between these two curves, all of this. In Calculus 1, we learned about Riemann sum. That means in that Riemann sum, the concept was split this interval a to b into infinite number of intervals. That you cannot visualize that easily. So suppose we were to split this into just a few finite number of intervals. Make up rectangles, it said, and find the area of each of those rectangles and add them up. If you do that, you have at least a ballpark figure. You have an approximate value of the area between the two curves. And then as an extension of it, suppose you could split this into n intervals and you figure out a formula for the sum of the areas of those n rectangles. The next step is to just take the limit of that area of n rectangles as n approaches infinity. And in that case, what you get is the exact area. And then they said, if you were to do that, that is exactly the same as the integral from a to b of f of x dx in Riemann sum, if you're looking at the area under the curve. So that is something precisely what we will do here. But this is a slightly different way of looking at Riemann sum as well. And that is, instead of splitting this into infinite number of rectangles, we'll take this approach. Suppose we were to construct a representative rectangle like this, okay, a vertical rectangle, and we put this at a location x from the origin, and the width of the rectangle is dx. Then we could move this rectangle. We'll initially place it all the way at the left, find out what the area of that itty bitty rectangle is, then scoot it to the right a little, figure out the new area of that new rectangle, add it to the previous area, and scoot it again, figure out the area, add to the previous sum. So instead of splitting this interval into infinite number of rectangles and all that stuff, why don't we think of it as making one rectangle and scooting it all the way from left to right? The concept is still the same. And in fact, this is a slightly better concept because most people in business, that is physicists and engineers, in fact, do think along this line. Hey, are you integrating along X or along Y? They would say. And that's a wonderful way of looking at it because in Calculus 3, you would in fact be talking about integrating not along X or Y, but along a curve. So that's possible. Those of you who will take physics 2 pretty soon, you will notice that you would be integrating along a curve in certain cases. So because of the advantage of thinking of it that way, I'm going to approach finding the area between the curves in this way, okay? So now let's examine. We will place the rectangle here, and we are supposed to find the area of that small rectangle, right? And let's say dA represents the area of that small rectangle. Can we find that area, dA? Yeah, notice the width of the rectangle. The width of the rectangle is dx. And If only we could get the height of the rectangle, we are in business. The height times the width should give us the area of this rectangle. So what is the height of this rectangle? Pay attention. Would you agree that the height of the rectangle is the y value at this point minus the y value at this point, right? But what is the y value at this point? Well, this curve is y equals f of x. This top point is actually a point on the curve y equals f of x. So if we happen to be at, say, x equals 2, right? That point has an x value of 2. In that case, the y value should be f of 2. If we are at x equals 3, that is the x coordinate of that point is 3, then the y value is f of 3. In our case, we happen to be at some arbitrary x, so the y value would be f of x. Similarly, the y value here at the bottom point would be g of x because the bottom point is on the curve y equals g of x. So f of x minus g of x should give you the height of the rectangle, the width is dx, and guess what? The differential area dA is nothing but f of x minus g of x times dx. You might ask, why in the world did I stick the absolute value sign around f of x minus g of x, right? That is to make sure that the height will always be a positive quantity. In this particular figure, I didn't have to worry about that because as we scoot the rectangle all the way from the left to the right, the f of x is clearly greater than g of x at all locations. So I didn't have to worry about it. But there could be situations where that may not be the case, especially let's say this one curved down like this and this one curved up like this. In that case, over a certain interval, f would be bigger than g, and in certain other interval, g will be bigger than f. At that time, you better make sure to stick an absolute value sign so that the f of x minus g of x or g of x minus f of x will always turn out to be positive. So that's one thing to keep in mind. Okay, so a little bit of a summary. The moment you run into a area between two curves problem, the first thing you have to do is draw the representative rectangle and immediately show the distance x from the origin, or in this case, from the y-axis to one of these points on the rectangle, and also show dx. The moment you do this, you are indicating to everybody that you are integrating along x. Okay? Now, how do you find the actual area of this one? Once you got the differential area, all you need to do is integrate. Integral of dA is A, right? And so when we to find area A, we integrate dA. That is, we integrate absolute value of f of x minus g of x times d of x times dx from A to B. As simple as that. Okay. Now let's look at another case. What if we were to have two curves that look like this? X equals f of y and x equals g of y. So let's pause for a second. Why in the world am I calling these curves as x equals f of y and x equals g of y? Or couldn't I call them y equals f of x and y equals g of x? The answer is no, I cannot. Because, as you can see, this curve, x equals g, the left side curve, fails the vertical line test. That means if we draw a vertical line, that vertical line, is cutting the graph at more than one point, which is a no-no for a y equals f of x type of curve, right? However, this does pass a horizontal line test. I don't happen to have one, but I could have illustrated with that. If we draw a horizontal line no matter where, that horizontal line will cut this graph at most 1 point, at a maximum of 1 point. If we draw it somewhere in the bottom here, well, it won't even cut the graph, and that's okay. But if it does cut, as it would if we were to place a horizontal line here, it must cut the graph at maximum of 1 point. And because this passes a horizontal line test, it's perfectly all right to call this as x equals some g of y. And similarly, this as x equals f of y. Okay? All right. So we have two curves, x equals f of y and x equals g of y. We need to find the area between these two curves. Now you may say, hey, what's the big deal? We could actually do what we did before. That is, we will draw a representative rectangle vertically like this. We'll place it all the way at the left end and we will integrate along x, right? Not so straightforward. One problem that you would bump into is, notice what the height of the rectangle is. If we happen to be anywhere, say from here to there, just about, the height of the rectangle is given by the x equals g of y curve, the top part of the curve minus the bottom part of the curve. However, if we continue to move over this region, unfortunately, the height of the curve is not given by the top part of g of y minus the bottom part of g of y. Instead, we are governed by two completely different curves or two line segments like that. And if we continue to move further to the right, over here, the top part of the curve x equals f of y to bottom part of f of y is how we find the height of the rectangle. You know the implication of this? The implication is we would have to split the integral into three different parts and go from all the way from the left end to the right end. And that's going to be a pain. Not only that, you have to figure out what this y equals f of x would be for the top part of the curve and another y equals f of x to the bottom part of the curve, because those top parts and just the top part and the bottom part could be written as some y equals g1 of x and y equals g2 of x. But you cannot just simply treat this as y equals f of x like I explained before. So you would have to go through that additional piece of work. And similarly for this one, you would have to figure out what the corresponding y equals f of x is and y equals f1 of x and y equals f of 2 of x for the bottom part and all this nonsense. So it is not a good idea to do this. Instead, if we were to make the rectangle a horizontal rectangle, things become so much more easy. That is, we'll make the rectangle horizontal. We will say that we have placed it at a distance of y from the origin or from the x-axis, and the should I call it width of the rectangle? In this case, because that dimension is more like a height, I'll say the height of the rectangle is dy, itty bitty dy, a differential height. As a result, we would have a differential area for this one. Okay, so we have a small itty bitty rectangle with an area of dA is located at a y value of y. And the question is, could we find dA so that we can integrate it to get the total area between the two curves? Let's try to find out. The height is dy, that's the easy part. What in the world is the width of the rectangle? Please pay attention to this part. Would you agree that the width of this rectangle is the x value at this point minus the x value at this point? Okay, What is the x value at this point? Well, that point happens to be on this curve x equals f of y. Y is a known quantity, is the independent variable, which means we can make it to be whatever we want. So we would know the value of y. And since this is x equals f of y curve, we can figure out precisely what x is of this point. The moment we know y and the moment we know f of y, we know exactly what x is. Similarly, for this point, we can find the x value. So the x value at this point minus the x value at this point should give us the width of this rectangle. And again, in order to make sure that this dA would be a positive quantity, the width would be a positive quantity, we'll stick an absolute value around it. Okay, absolute value of f of y minus g of y times dy. And in order to find the total area, we will integrate from y equals c to y equals d. That's a small difference. We are integrating along y, so we are integrating from bottom to top, and so the bottommost point has a y value of c, right? And the topmost point has a y value of d. So in the integral, we see y equals c to y equals d. As simple as that. Okay, I'm going to work a few problems to solidify this concept, and that's going to be part two.